Okay, so in this video, we will study the following alternating series. First, to get a feel for it, let's expand out the first few terms of the series. So when n equals 1, we obtain negative 1, plus when n equals 2, 1 over 2 cubed, which is 8. When n equals 3, negative 1 over 3 cubed, 27. Plus when n equals 4, 1 over 4 cubed, 64. Plus when n equals 5, negative 1 over 125, and so on. So we have a classic alternating series as the terms that we are summing alternate systematically between negative and positive. The first question, of course, to ask is, does this series converge or diverge? So we will apply the alternating series test. So we have to consider Bn, the terms that we are trying to sum in absolute value. So in absolute value, the terms of our sequence are quite simply 1 over n cubed, as negative 1 to the n in absolute value is equal to 1. Now obviously as n tends to infinity, Bn tends to 0. And as Bn is a constant over an increasing function, the result is obviously a decreasing function. So as Bn is decreasing, therefore obviously eventually decreasing, and approaches 0 as n tends to infinity, both conditions for the alternating series test are met, and so this series converges by the alternating series test. And again, the word converges means that if we sum all of the terms of the series, we will obtain a unique real number. Now we may not be able to get the exact value of this infinite series. If we can, great, but that is not always the case. So let me write down now the infinite series again. As it converges, this is a unique real number. If we cannot find the exact value of this infinite alternating series, we may settle for an approximation by summing the first few terms of the series. How many terms? Well, we could sum the first 10 terms, the first 100 terms, the first million terms. Let's leave the number of terms that we sum as an arbitrary value, uppercase n. So this is the truncated sum of the infinite series, summing from the first term up to the uppercase nth term. For any choice of n, whether it's 10, 100, and so on, this will be an approximation to the exact value of the series. Naturally, we would ask, how good is this approximation? How close is the approximate value, the truncated sum, to the exact value, the infinite series? Well, this is of course measured by the difference between the approximate value and the exact value. So we subtract the two, and we take the absolute value of this difference. This is what we call the error of the approximation. The difference between the exact value and the approximate value in absolute value is the error, and we ask, or can we quantify how good this approximation is in terms of how many terms we have summed. And we have a remarkably simple and elegant result that gives us an upper bound for the error coming from the alternating series test, what we call the error estimate. If we sum up to the uppercase nth term of the error of the approximation is at most, so smaller than or equal to, the first omitted term in absolute value. Well, if we sum up to uppercase n, the next term will be at uppercase n plus 1. In absolute value, this is Bn, so the first omitted term in absolute value will be Bn plus 1. In our case, this is 1 over uppercase n plus 1 cubed. So So if we sum up to the uppercase nth term, the error of the approximation is at most 1 over uppercase n plus 1 cubed. And of course, you can see, we can make this as small as we want by taking n to be sufficiently large. So now what if we have an accuracy in mind? What if, say, we want the approximation to be no further off from the exact value than, say, 10 to the negative 12. So we have a target level of accuracy. We want to make sure that we sum enough terms of the series to guarantee the error to be smaller than, say, 10 to the negative 12. Well, if we make the upper bound less than 10 to the negative 12, then this of course works, right? If the error is always less than 1 over n plus 1 cubed, and we choose n to be sufficiently large to make this less than 10 to the negative 12, then the error obviously will be also less than 10 to the negative 12. And this can of course be achieved since as n can be made arbitrarily large, 1 over n plus 1 cubed can be made arbitrarily small. So no matter the level of accuracy that you need, you can always choose n to be large enough to satisfy this requirement. And now let us solve for uppercase n. First, I will rewrite this by sending this down to have a positive exponent. So this will give me 1 over n plus 1 cubed must be smaller than 1 over 10 to the 12. As both sides are positive, I can invert both sides. So I take the reciprocal of both sides. This of course will change this, the direction of the inequality. If this is smaller than this, then 1 over this will be larger than 1 over this. To get closer to solving for n, we cancel the cube by taking the cube root of both sides. So n plus 1 must be larger than 12 over 3 is 4, 10 to the 4. And finally, subtracting 1, n must be larger than 10,000 minus 1. We can make this become an inequality that can allow for inequality. If n is strictly larger than 10,000 minus 1, then n must be at least as big as 10,000, 10 to the 4. And now we have our answer. If we ask how many terms of this series must we sum so that our approximation is accurate with this error bound. So if we want the error of our approximation, the difference between the approximate value and the exact value, to be smaller than 10 to the negative 12, well, in this particular case, we have to sum at least the first 10,000 terms. And again, we could have changed the 12 here for 100 and have a different lower bound for n. And as the error can be made arbitrarily small, no matter the accuracy level that you desire, you can always choose n to be sufficiently large to meet the desired accuracy of your approximation. So here, with summing the first 10,000 terms of this series, we have a remarkably good approximation, as the difference between our approximation and the exact value and absolute value will be smaller than 10 to the negative 12. So a really, really small error. And that's it.